All right, let's get right into it. We're going to tackle energy changes in chemical reactions, breaking down exactly what exothermic and endothermic mean, so you can absolutely nail this topic for your A-level chemistry exams. Let's do this.
So think about this for a second. A campfire. It obviously warms you up, but an instant cold pack? It does the complete opposite. They're both just chemical reactions, so what is going on here? That's the big question we're answering today, and it all boils down to the flow of energy.
Now, to talk about this energy flow like a proper chemist, we need a specific name for it. And that name is enthalpy change. It's pretty much how we measure the heat that's being exchanged in a reaction.
So, what is enthalpy change exactly? Well, you'll see it written as this symbol, delta H, and all it really is the amount of heat energy that's either given off or taken in during a reaction. The one key thing to remember is that we measure it at a constant pressure. That's super important because it makes sure all our results are consistent and comparable, you know? It's how most lab experiments are done anyway.
Okay, so when it comes to energy, every single chemical reaction plays for one of two teams. Let's meet the two big players, exothermic and endothermic.
This slide is basically your cheat sheet. The easiest way to remember this is that exothermic reactions let energy exit the system. Heat is released, so the surroundings get hotter, and because the system itself is losing energy, its delta H value is negative. Now, on the flip side, endothermic reactions pull energy in. The system absorbs heat from the surroundings, so they get colder, and since the system has gained energy, its delta H is positive. Simple as that.
Exothermic reactions? Oh, they're literally everywhere. Combustion is the classic example. Burning anything, from the gas in a Bunsen burner to the fuel in your car, releases a ton of heat. Another great one is neutralization. Anytime you mix an acid and a base, it releases heat. You can actually feel the beaker get warm. And on the other side of the coin, we have endothermic reactions. They might seem a little less obvious, but they are just as crucial. Think about thermal decomposition. That's when you have to use heat to break a compound down. And maybe the most important endothermic reaction on the entire planet, photosynthesis. Plants are literally taking in light energy from the sun to build glucose. They're storing that energy right inside the chemical bonds.
Okay, so we know what happens, but why? Why do some reactions release energy and others absorb it? Well, the whole secret, the real key to understanding this, is all about the chemical bonds themselves.
This right here is the heart of it. Let's think about energy like it's money. To break the bonds in your reactants, you have to put energy in. It's a cost. You're making an energy withdrawal. But when new, more stable bonds are formed in the products, energy gets released. That's your payout, your energy deposit. The overall reaction is just the final balance in that energy bank account.
Let's lock this idea in. Breaking any chemical bond, it doesn't matter which one, always requires you to put energy in. You have to spend energy to pull those atoms apart. And that makes bond breaking, by itself, an endothermic process.
And on the flip side, when atoms come together and form new bonds, energy is always released. This is an exothermic process. Think of it as energy being paid back to the surroundings as the atoms settle down into a nice, stable arrangement.
So when it all comes down to it, whether a reaction is exothermic or endothermic is really just a matter of simple accounting. It's the final balance between the energy you spent breaking old bonds and the energy you got back making the new ones. And this is the formula you absolutely need to know for your exams. The overall enthalpy change, delta H, is the sum of all the energies for the bonds you broke, that's what that little sigma symbol means, minus the sum of all the energies you got back from the bonds you made. If the energy you get out from making bonds is more than the energy you put in, delta H is negative and you've got an exothermic reaction.
Doing the math is great, but sometimes the best way to really get a feel for the energy journey of a reaction is to actually see it. And that's where these reaction profile diagrams are so useful. Just look at these two side by side. The most important difference to spot is the finish line. See how in the exothermic one on the left, the products finish at a lower energy level than where the reactants started? That's because energy has been released. But in the endothermic one on the right, the products are way up high. Energy has been absorbed. Let's zoom in on the exothermic profile. You always start with your reactants. Now notice you have to put a little bit of energy in to get things going. That hump is called the activation energy, or EA. It's the minimum energy needed to kickstart the whole thing. But once you get over that hump, the products form and release a whole bunch of energy, ending up at a much lower, more stable state. That overall drop from start to finish, that's your negative delta H. And now for the endothermic profile. See how the products are sitting higher up on the energy ladder than the reactants? This picture shows you, clear as day, that there was a net input of energy. The reaction had to keep taking in energy to even happen, and that's why your final delta H value is positive.
Okay, theory's done. Now it's time for a rapid-fire rundown of exactly what you need to have locked in your brain for exam day.
These are your absolute must-knows. First, standard conditions. That's 298 Kelvin and 100 kilopascals. You need to know these so we can make fair comparisons. Second, the signs. Delta H is negative for exo, positive for endo. Got it? Third, the bonds. Breaking is endo, making is exo. And finally, don't forget that formula. Delta H equals the energy for bonds broken minus bonds made.
All right, time for a quick test. The combustion of methane. What do you think? Well, it's combustion, it's burning. It gives off heat. So that makes it exothermic. And the sign of its delta H has to be negative.
Question 2 for you. A reaction has a positive delta H value. What does that tell us? If delta H is positive, that means the system has gained energy, so it must have absorbed heat from the surroundings, which makes it an endothermic reaction.
Last one. Let's say you get more energy out when you make the new bonds than you had to put in to break the old ones. What's the bottom line? Well, if more energy is released than absorbed, there's a net release of energy. That means the reaction is exothermic, and its overall enthalpy change is negative. You got it?
So what's the big picture here? This whole energy balance thing, this idea of breaking and making bonds, it isn't just some abstract concept for an exam. It's fundamental. The exothermic reactions in fuel are what power our world, while the endothermic magic of photosynthesis is what sustains pretty much all life on Earth. It's that important.
And that brings us to the end. I'll leave you with one final thing to think about. Now that you know the rules, what about an everyday process like water freezing into ice? Is energy being absorbed or released? What about baking a cake? What other things do you see every day that you can now look at through the eyes of a chemist? Thanks so much.